All right, good afternoon. Just looking at picking up where we have left off, and we've been looking at multiplying polynomials as well as factoring, and also we have been looking at combining like terms, whether the terms were direct or expressed as fractions. And then we cross over into looking at equations, looking at the categories involving types of equations, as well as just starting looking into quadratic equations. And just looking into the categories where we have conditional, contradiction, as well as identity. Again, a conditional is going to have a limited number of solutions. A contradiction is going to have no solution on the basis that the framing is done in such a way that the result is trying to say that two quantities are said to be equal to each other when in fact they are not. And an identity ends up with an infinite number of solutions on the basis that we have the equation to result as two quantities said to be equal to each other, and in fact they are. And regarding those three categories, we have on page 68. And now last week we've been looking at, from the textbook problems, working out equations in all types of variables, and it looks as if today is going to be a bit of that history repeating itself. And for what we have on page 68, we have for number 24, we are looking at trying to solve for the variable n, and looking at what we have here. We've got 4 times the quantity of 3 minus 5n, followed by the addition of 1 is equal to negative 4n minus 8 minus 16n, and looking at removing the parentheses and gathering our like terms in this equation. We have first of all 4 distributed over the quantity of 3 minus 5n, so we're going to have 12, and 4 over negative 5n is going to be a negative 20n, followed by the addition of 1. And to the right, we have negative 4n minus 8 minus 16n. The variable terms we have to exist are negative 4n and negative 16n. Combining these two, we have negative 20n minus 8. And for what we have in the next step, we have like terms with the constants 12 and 1, and we can join those together. So we will have 13 minus 20n is equal to, and we already have negative 20n minus 8. So those are unlike terms on the right hand side. Now for what we have at this stage, we're going to have like terms on opposite sides of the equation. And here we have with 13 minus 20n set equal to negative 20n minus 8. We can combine like terms, whether it is gathering the variable terms or the constants. And looking at trying to solve for n, see what it is perhaps a more common mode to combine the variable terms, which we have at both negative 20n, and if we join these together, so I'm going to add 20n to both sides, and if I combine, it looks like we're going to have complete cancellation. And so what will be left standing will be two numbers, resulting in the statement where we have 13 is equal to negative 8. Now here we have two quantities that are said to be equal to each other when in fact they are not. 13 and negative 8, they're not exactly the same thing, and so we have a false statement. And for what this means in terms of n, you could plug in any value for n, whether it's a 0, a negative, or any positive value, and you're not going to have both sides to end up as equal amounts. And so in this case, we're going to have no solution for n. They could try all the combinations of values of n, but you're not going to have both sides to equal. So you have no solution. And when you have an equation that results in a false equality statement, okay, this particular instance falls under the category of contradiction. Now we have, in the case of the next item, we have for number 26. Okay, so we're looking at trying to solve for n to trying to solve for x. And in the case of what we have for 26, we have this equation where on the left, okay, we have -5 plus 3x is equal to 3 times the quantity of x minus 1 followed by the subtraction of 2. And looking at removing the parentheses. Alright, so we have unlike terms on the left hand side, so nothing to combine on the left, and we have to the right, we have 3 times the quantity of x minus 1, so we're looking at distribution, multiplication over subtraction. So we've got 3x, and 3 over -1 will be -3, and we have the -2 to follow. Again, we have -5 plus 3x on the left hand side. And for the activity to the right, after distributing, we have 3x, and combining the constants, -3 and -2, okay, we have at -5. Okay, so here we have -5 plus 3x equal to 3x minus 5, just like what we had earlier. We got two variable terms that are separated, and also constants that are separated. So we are re-entering this particular phase, and to see how the follow-through is going to be, and just as we combine terms in the variable n, we're going to combine in the variable x. So what I can do here is move 3x upon subtracting on both sides, and once again we'll have cancellations of the variable terms. And this time around, in spite of having two numbers to remain, unlike what we had with the false equality statement in 24, it turns out that in 26 we have a true statement for -5 and -5 are the same. And this signals that you can plug in any value for x, whether again it is 0 or any negative or positive, whether it's a whole number, a fraction, a radical. You're going to have both sides, okay, to be the same. And so for what we have in this case, we're not going to have just one solution, but an infinite number of solutions. And in this particular case, right, for x, the solution is going to be the set of all real numbers, and this will be written as R. And as Alex likes to put it, okay, another representation of the entire real number system will be the set of all real numbers. And you can write this with negative and positive infinity in the parentheses, and with both sides equaling each other. Out of the three cases, we have an identity. Again, if you have two numbers left standing and they are equal to each other, it's an identity. Otherwise, if they are not equal to each other, we had the statement to end up as a contradiction. Now, in the case of what we have with number 28, this time we're looking at solving for y. And in terms of how to approach this one. You can keep the fractions and gather the terms, or you can also rewrite the equation in terms of where all the coefficients will be integers. Now for this problem, we're looking at trying to solve for y, whereupon we have 2/3 of y minus 5 is equal to 1/6 of y minus 4. And again, you could gather together the y terms even in fractional form and separate or isolate from the constants. That is one way. But if one is not a particular fan of working with fractions, they can multiply all the terms out by the least common denominator of the fractions. Here we have 2/3 as a coefficient in the fraction on the left, and to the right I have 1/6 as a fraction. And if I take care, let's say of just the fractions, you have the least common denominator will be the smallest number that both 3 and 6 will go into, and so that is going to be 6. So if I, in a sense, hit the reset button, it's going to change the coefficients, but it's not going to change whatever potential solution there is for y. So if I multiply the terms all out by 6, okay, so we have 6 times 2/3 of y, and we can go ahead and bring down the subtraction, so we have minus 6 times 5. Okay, so we have 6 times 1/6 of y. And we have minus 6 times 4. Okay, so you have 6 times 2/3 of y. Okay, and you can do a little bit of cross multiplying, or if you were to just combine, you could look at this as 6/1 times 2/3 of y. So we would have 12/3 of y minus 30 is equal to, let's say we have 6/6 of y minus 24, and 12/3, okay, that becomes 4y minus 30. 6/6 is 1y, so I have y minus 24. Okay, now again we have two variable terms apart as well as constants that are separated. And this time around, we're not going to have the same variable terms. And we can still combine what we have in the letter y. And my recommendation is that if you're working with an equation and you don't want to work with negative terms any more than is necessary, I would take out the smaller of the variable terms. So between 4y and y, okay, the lesser of the two will be y. So I can follow through and subtract y at both ends. And we're going to have here 4y minus y becomes 3y minus 30 is equal to negative 24. And for what we have in terms of following through, okay, so you got 3y minus 30 is equal to negative 24. And if I isolate the y term, which we have with 3y, I can add 30 to both sides. And so we will have that 3y is equal to negative 24 plus 30, which is 6. And 3 will go completely into 6. And so 3 times y is equal to 6. Okay, we're going to have that y is equal to 2. And alright, so you have not a situation where you have no solution, as was the case with this contradiction in number 24, nor do you have an identity, for we still have the y left standing, and this is equal to 2. And what this means is that this equation will work on the condition that y is equal to 2 and only 2. And so an equation that has a limited number of solutions is a conditional, and that is exactly what we have for number 28. Okay, now in the crossover, okay, to what we have with the next set of items, and this is with quadratic equations. And there are various approaches that can be undertaken in terms of solving quadratic equations, and we had looked at the zero product property. And first of all, let me mention, okay, for a quadratic equation, again, we had that the standard form was ax squared plus bx plus c is equal to 0. Okay, that's the standard. Okay, but the quadratic equation is not necessarily limited to the variable x. Okay, you can have other letters. And number 30 is going to present such a case where we are looking at not solving for x, but instead solving for y. And in 30, okay, we have that y squared is equal to 18 minus 7y. And if you notice, this equation is not exactly set equal to 0. And we have the highest order term in the variable to be y squared, which is situated by itself on the left hand side. But we can set this equation to 0 and keep y squared where it is on the left, so we can move both the 18 and the 7y so for what we have now, and putting the terms in decreasing degree order, so you have y to the second, and we have plus 7y minus 18 is equal to 0. Okay, so we have a standard form. So you have like just changing the variable x to y. You have ax squared represented by y squared, and plus bx represented by plus 7y, and we have the constant c to be at negative 18. Now, in this trinomial that is formed and set equal to 0, we can factor. And just as we have had x squared to be factored to x and x, y squared can go to y and y. And in terms of the factors of interest, now we're looking at those numbers that will multiply into negative 18, and that will have some or difference on the plus side at 7. So negative 18 have factoring out to a plus and minus factor, and since the middle coefficient is a positive 7, okay, we're going to have more weight applied to the addition than to the subtraction. So you're going to have, in this case, you have plus 9, and on the minus side we have 2. 9 times negative 2 is negative 18. 9 and negative 2 amount to still being on the plus side at 7. And with the follow through that we have with the zero product property, so this statement is 0 if the factors at least have one of them to be 0. And so in pinpointing what the potential solutions and y could be, we have at the one end we have y plus 9 is equal to 0, and on the other we have y minus 2 is equal to 0. And if y plus 9 is equal to 0, we're going to have that y is equal to negative 9. And if y minus 2 is equal to 0, okay, we'll have that y is equal to 2. So in a sense, number 30 would be a case of a conditional, meaning that this equation is true on the condition that y is either of these two values. Okay. So we have for the possible results here, we have negative 9 and positive 2. And you can do a bit of a verification. Okay, so if I were to go back to the original equation, say if I have y at 2, Okay, so y squared at 2 squared. 2 squared is going to be 4. To the right, I have negative 7 times 2 is negative 14. 18 and negative 14 will also be at 4. 4 is equal to 4, so 2 would check out. Now for negative 9, okay, let's say if we look on the right, negative 7 times negative 9 is going to be a positive 63. 18 and 63 is going to be 81. And for negative 9 squared, like negative 9 times negative 9, that is also 81. And so negative 9 would check out. So those two values will make this equation ring true, once again, at those amounts. Okay. Now, in the case of what we have with quadratic equations, and we're still are looking at working with the zero product property. Okay, now we're going with, once again, a different variable, and this time we're looking at solving for z. Okay, here we have z squared is equal to 25z, and we have a quadratic equation, okay, thanks to the higher order in term, make that the higher order term in z to be z to the second. And just like y squared earlier, z squared is by itself, and I can move whatever's on the other side over. In this case, 25z. So if I subtract, okay, we're going to have establishing this equation in standard form. Okay, so I have z squared minus 25z is equal to 0. All right, so just sort of backpedaling a bit. Okay, so if I change the variable x to z, so you have like ax squared is represented by z to the second, bx, okay, had to be represented by the negative term minus 25z. And if you notice, we don't have a constant to immediately follow and to exist in front of the equal sign, so that c would be at 0. Now if you notice with z squared minus 25z, okay, now this is factorable, but it is not going to be factored into binomials exclusively. One might be thinking, okay, why can it not be z plus 5 and z minus 5? Well, the reason for this is because of the z alongside the 25. Now if I had the statement to be z squared minus 25, then you would have unequivocally a difference of squares. But in z squared minus 25z, okay, I have a different pathway. Notice that the terms have greatest common factor with the letter z. So we have z factored out, and taking into z squared minus 25z, we have z minus 25. So we have z and z minus 25 as the factors. And if I set these to 0, okay, so I have z is equal to 0. For the other factor, z minus 25 is equal to 0. We're going to have that z is equal to 25. And you can check out, okay, we got 25 times 25, and 25 squared is also 25 times 25. So both sides, okay, will be at 625. So 25 would check out, and with 0, 0 squared is 0, 25 times 0 is 0. And so those are going to be the only values to which this equation will ring true. So we have, again, kind of a conditional, where we have the restriction to be that z has to be 0 or 25 to satisfy this equation as ending up as a true statement. Now, regarding the zero product property, okay, 35 presents a special case here that further stresses when you're using the zero product property, you must have the product of the factors to equal 0. And here we have in the presentation, okay, once again going to yet another letter. With the variable m, we have the quantity of m plus 4 times that of m minus 5, okay, is equal to negative 8. Okay, now I would like for it to be as such, to be able to go ahead and set m plus 4 and m minus 5 equal to the constants on the other side. But with the number -8, I can't do that. Okay, so that -8 must be 0. For us to use the zero product property. Alright, so if I can't set m plus 4 or m minus 5 to -8, okay, that means that I have a bit of an entanglement. And to undo this kind of situation, I'm going to have to untangle by foiling out what we have in m plus 4 and m minus 5. So with the FOIL, okay, we have m times m, first product is m squared. Outside product, we have m times -5, so we have -5m. Inside product, we have 4 times m. And we have 4 times -5 is -20. And we have is equal to -8. So I have a quadratic equation in the variable m, and getting this closer to expressing in terms of the standard form. So we got m squared, and gathering together -5m and 4m, okay, we have a minus m, we have -20, and we have is equal to -8. And I can set the equation to 0. But first, I had to move this -8 over, and to get rid of its presence, I'm just going to add 8 to both ends of the equation. And we're going to have in the rewrite, okay, we have m squared minus m, -20 plus 8 comes out to -12, and we have is equal to 0. Okay. So in the conversion to where this equation, which was originally set equal to -8, to where it is going to be set to 0, okay, we got this standard form of the quadratic equation for the variable m, and now I can factor. And this time around, okay, we have m squared goes to m and m, and factors of -12. One is going to be positive and the other is negative, where the sum or difference, okay, will be at -1, the middle coefficient. So we're going to have slightly more weight given to the subtraction than to the addition. And in this case, we're going to have m plus 3 and m minus 4. Okay, 3 times -4 is -12. 3 plus -4 is -1. Okay, and we have the product at 0, and I can set this time, or putting into effect, the zero product property. For this time, the equation is equal to 0 as opposed to -8. Okay, so if I set m plus 3 as well as m minus 4 to 0, we're going to have respectively m equal to -3, and also we have m equal to 4. And you can go back and check the results for m at -3. -3 plus 4 is 1. -3 minus 5 is -8. 1 times -8 is -8. So m equals -3 checks out. For m is equal to 4. 4 plus 4 is 8. 4 minus 5 is -1. 8 times -1 is also -8. Okay, so for this one, okay, we have m equal to -3 at the lower end, and we have the other possible value at the upper end with m equal to 4. Now, again, the zero product property is one approach that can be taken potentially in solving for a quadratic equation. For problems like this, we had the coefficients aligned, okay, such that factoring and using this approach is feasible. Okay, but it is not the only way, and the zero product property is not always the most direct approach. And there is another situation or type of scenario that can be conducted. And this is going to be what we have with the square root property of equality. For a lot of the problems where you could use this, it could be almost like rock, paper, scissors, whether to go with this property or the zero product property. And then there are those situations where you might have the coefficients to be such that, the problem is not quite so factor friendly. Let's go with the square root property of equality. All right, so we have had throughout so far for solutions. Okay, we've had revolved about the real number system. And for the square root property of equality, let's say that in general terms, it's not limited to just the variables x and p, but just as a general representation. Say that if you have that p is a non-negative value, meaning that p could be 0 or higher. If p is a non-negative value, and we have that x to the second is equal to p, then that means that x can have up to, not always, but potentially up to 2 possibilities, where you have the x is equal to plus or minus the square root of p. Okay, so you have, if x squared is equal to p, p being a non-negative value, then you're going to have the x is equal to plus or minus the square root of p. And let me give you just some backdrops here. Say if you're looking at solving for x, let me say I have by SRP. So we'll have for square root property. And we'll say we have, like in one case, we'll say we have as something that is that could be factored. Say if you have a difference of squares, whereupon you have x squared minus 36 is equal to 0. And if your reflex is such that you would say x plus 6, x minus 6, apply the zero product property, set each of the factors to 0 and get your values of x, that is one way. But if you're to go with the square root property of equality, what you can do here is that with this equation, we can get x squared by itself upon adding 36 to both sides. And so we had the x squared is equal to 36. Okay. So we're at this stage. Okay. So you have x squared by itself, and that representing p, okay, would have to be at 36. And if I drop from x squared to x, if I do this in accordance with the square root property of equality, that represents p. We're going to have carried out its positive and negative square root layout. So you have x is equal to plus or minus the square root of 36. Now 36 is a perfect square value. And the square root of 36 is 6, but now for the values in x, by the square root property of equality, we have negative 6 included as a possible solution. So we have the x is equal to negative and positive 6, and you can check square root of negative 6 is negative 6 times negative 6, which is 36, minus 36 is 0. Also 6 squared is 36 minus 36, also at 0. Now, another case here where you might not have the problem to be as factor friendly. And let's say that, just still staying with the variable x, if we have 3x squared minus 51 is equal to 0. Now, again, we have a little bit of a run-in. You could either divide by 3 or just go ahead and separate the variable term. No one right way in this case. But we're going to get the x squared ultimately by itself. And I'll tell you what, we'll add 51. And we have 3x squared is equal to 51. And reframing this, okay, to take care of the multiplication by 3 upon division by 3 at both ends. Okay. So you got 3x squared over 3 becomes x squared. 51 divided by 3 becomes 17. And so we have x squared equal to p, represented by x squared is equal to 17. And if I go from x squared to x and have the plus or minus the square root of p representation, we have x equal to plus or minus the square root of 17. And if I leave the results in exact terms, well, square root of 17 is a prime number, or the square root of a prime number, and those values will already be in their simplest form. So we have x equal to the square root of 17 at the upper end, and at the lower end we have that x is equal to the opposite value, which we have with the negative of the square root of 17. So you're looking at like 4 point something as well as minus 4 point something. Now, just kind of mentioning with the square root property of equality, again, for that which represents x into x squared, we're not just limited to just the single letter x. It can also be a different letter. It can also be a multi-term expression that is being squared. And I'll give you a bit of a quick case here. Let's say that if you're looking at solving for x, whereupon we have, let's say we have x minus 4 raised to the second is equal to 25. Okay, so we're kind of in the realm, okay, whereupon we have x squared is equal to p, where we have x projected out to x minus 4, and p we had to be at 25. And as we go out to x is equal to plus or minus the square root of p. So I'm going from the square of x minus 4 to x minus 4. Okay, so going from second degree to just first degree. I don't need the parentheses, but just to kind of show you the transition here. So we're going from second degree in the expression to first order, and p we have at 25. And we have going from second to first degree in the binomial x minus 4, we have equal to plus or minus the square root of 25. And 25 is a perfect square value. And square root of 25 is going to be at 5. So we have that x minus 4 is equal to plus or minus 5. And we're still looking at solving for x. Okay, and so how do we do this? Well, we're going to have a system of equations. Okay, and we're involving 5 and negative 5. So we're going to have at one end, we're going to take x minus 4 and set equal to negative 5. And the other possible scenario is whereupon we have the x minus 4 is equal to 5. And if I'm looking at solving for x, so for x minus 4 equal to negative 5, if I add 4 to both ends, okay, so we're going to have the x is equal to negative 5 plus 4, which is going to be at negative 1. And I can just check for a bit of consistency. So if x is negative 1, go back to the original equation. Okay, so with x at negative 1, negative 1 minus 4 becomes negative 5. And for the square of negative 5, we have negative 5 times negative 5, so we have a positive 25. So negative 1 checks out. Now for x minus 4 equal to 5, if I solve for x in this scenario, okay, we're going to have that x is equal to 5 plus 4, which is going to be at 9. And with x at 9, 9 minus 4 is 5. And 5 squared is going to be 5 times 5, which will also be 25. So these values will check out. And so you have x at negative 1 as well as 9. And just looking at what we have with the square root property of equality. And I'll tell you what, for the next few moments, okay, say we have solving by the square root property. Okay. One or two of these, okay, might be a little bit tricky, but so we have, first of all, we have 2x squared minus 200 is equal to 0. And say we have next, okay, we'll say we have 2x squared minus 54 is equal to 0. And let's say that where we have binomial expression. Okay, so what? Let's see what we get for x whenever we have the square of x plus 4 minus 37 is equal to 0. So be looking at these three items, and we'll discuss in a few minutes. Alright, just one other thing too. I know that in Alex is big on radical reduction. Like if you're looking at the square root of a number that's not a perfect square but could be the multiple of a perfect square greater than 1. Okay, and let's say that for what we have in the first item, okay, we have solving for x. Okay, we have 2x squared minus 200 is equal to 0. And if we look at, you could either divide the equation by 2 and just say we have x squared minus 100 is equal to 0, and then just separate the variable terms. That is one way. Or it could just go ahead and add and then divide. Either approach works, or either sequence is going to work. Okay, so we have for 2x squared set equal to 200. Again, you could divide by 2 first and then add. Whichever pathway you choose, okay, is going to lead to x squared is equal to 100. Okay, so you have x squared is equal to 100, and from this, okay, we have x squared is equal to p to be represented by x squared is equal to 100, and for the follow-through, in terms of the square root property of equality, we have x equal to plus or minus the square root of 100. 100 is a perfect square value, and the square root of 100 is 10, and the square root property of equality includes that amount as well as its opposite, or in this case its additive inverse. So we're going to have two solutions that will work, okay, one positive 10 and the other negative 10. Now the second item has sort of the same setup. Okay, you have 2x squared at the front, and you have a constant to follow with minus 54, and the equation is set to 0. Now we're looking at solving by the square root property of equality. So you're going to be getting the variable term or expression by itself. And right now we have the variable term to be at 2x squared. So I had that on one side, everything else on the other. This signals that I'm going to move the 54 Okay, so adding 54 to both ends. Okay, so we have 2x squared is equal to 54 and we have upon dividing by 2 okay, so we have dividing by 2. Okay, so we have 2x squared over 2. Okay, this will be x squared. Okay, so we have x squared is equal to 27. Okay, now this is a case of where reducing radicals will come to the forefront. Okay, so again, we have at this stage, we're going to have x squared equal to p, and converting p in terms of its plus and minus square root terms. Okay, so I have x equal to plus or minus, okay, the square root of 27. Okay, let me pause. Okay, we have with the square root of 27, okay, there's no whole number times itself, okay, that will give you 27. However, 27 in square root terms can be reduced. And what I mean by this is that for 27, okay, we have in terms of factoring, now square root of 27, there will be two numbers other than 27 and 1 that will go into 27, and those numbers will be 9 and 3. So for the square root of 27, okay, we'll have the square root of 9 times the square root of 3, and the square root of 9 is 3. Then we have times the square root of 3. And we have in reduced radical terms. Okay, so plus or minus the square root of 27. This will go to plus or minus 3 times the square root of 3. And if we look at itemizing, like in the case of Alex, okay, you have added to inverse solutions, and in exact terms, we have 3 times the square root of 3, as well as the negative of 3 times the square root of 3. I'll mention this, okay. I was going to bring this up. Okay, like you have in the case of perfect squares. Okay, like perfect squares. Okay, you have perfect squares like 1 times 1 is 1, 2 times 2, or 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25. We got 6 squared, 7 squared. Okay. You mentioned this. Okay, say if you're looking at reducing, in terms of a perfect square. Okay, so you have the square root of 500. Okay, now if you look at perfect squares that will go into 500. Okay, now the highest one of these is going to be at 100. Okay, so you have the square root of 100 times 5. Now you've got a perfect square number with 100. And you have separating, you have the square root of 5. And guess what? This would come out to 10 times the square root of 5. But now let's say that if you did not start out with the highest perfect square value among the perfect squares. Okay, among the perfect squares, you have not only 100 that will go into it, but also 25. Let's say you have the square root of 25 times 20. Okay, so 25 is a perfect square value. So we can set this apart from the square root of 20. Now 20 is an even number. Now it's not a perfect square, but if you notice 4 will go into it. So you have 25. Now for 20, 20 is going to be 4 times 5. Give me just a moment. So I got square root of 25 times the square root of 4 times the square root of 5. Square root of 25 is going to be at 5. Square root of 4 is 2. We have times the square root of 5. And putting together, we can come out to 10 times. Okay. It's kind of going back to okay, so you had the square root of 500. Notice you got the decimal layout at 22.36067 if you were to express in decimal approximation terms. And guess what? If I had like 10 times the square root of 5, voila. So 10 times the square root of 5 is going to be the reduced radical version of the square root of 500. And just like with the square root of 27, that number is almost 5.2. And guess what? 3 times the square root of 3. Now you gotta think about 3 square root of 3 is going to almost be just over 1.7. And guess what? 3 times the square root of 3 as a decimal approximation comes out to the same value. Yeah. So 3 square root of 3 is a reduced radical version of the square root of 27. And 10 times the square root of 5 is going to be the reduced radical version of the square root of 500. Think of it like this. Square root of 5 is about 2.24 almost. And 10 times that is almost like 22.4. And guess what? Square root of 500, you have right at that amount. So those are the dynamics that are played out in the case of yeah, for what we have. Okay, yeah, I can do that. I'll squeeze that in. If you've got something like, let's say okay, now we know that the square root of 49 is going to be at 7. Okay. Now let's say if we have something like the square root of, we'll just go down one. We got the square root of 48. Okay, so the square root of 48 is a number that is almost 7. It's going to be like 6 point something, some number over 6.5. Now for the perfect squares, okay, now the highest number that will go into 48, okay, 36 will not go into it, 25 won't go directly into it. Now 16 will go into 48 3 times. Okay, and 16, okay, this is in the family of perfect squares. And 3, well, 3 is not a perfect square value. And if I separate, we have square root of 16, okay, and then I have, square root of 16 times 3 would be the square root of 16 times the square root of 3. Square root of 16 is going to be at 4. Square root of 16 is 4, so you just remove the radical. Square root of 16 is 4, and we keep the square root of 3. Square root of 48 as a reduced radical will become 4 times, okay, the square root of 3. And I just mentioned, okay, so we have with the square root of 48, you have about 6.92. And you got 4 times the square root of 3. Okay, so you have that 6.92 number. Okay. So you have like square root of 54. Your perfect squares. Okay, 49 doesn't go into it, 36 doesn't, 25 doesn't, 16 doesn't, 9 does. So you got the square root of 9 times the square root of 6. Now I can, okay, remember the 9 here. 9 is a perfect square number. Oh, I know. You have like the square root of 9. That goes to 3. Square root of 9 is going to be a whole number. So you got 3. And the square root of 6, because 6 is not a perfect square, that stays in the radical. So you got square root of 54. You got 3 times the square root of 6. So again, 2 different ways of saying the same thing. 3 times the square root of 6 is going to be the reduced radical. So, okay, now for what we have in the third case. All right, so we have where we're taking the square root property of equality. And we have on this one, okay, so you have the square root of x plus 4 minus 37 is equal to 0. And if I get, let's say, the square root of x plus 4 by itself, okay, so if I add 37, okay, so I had the square root of x plus 4 is equal to 37. And if I go from second degree in x plus 4 to just first order, and for the p-value, I have plus or minus, okay, the square root of 37. And guess what? Square root of 37. 37 is a prime number. And I cannot reduce this, because the highest perfect square number divisible into 37 is only 1. It's going back to the perfect squares, like 4, 9, 16, 25, and 36. None of those other numbers will go into 37. So 37 is stuck where it is. Now, and looking at solving for x, say if I set x plus 4 equal to the square root of 37, and the way I can do this, for x plus 4 equal to plus or minus, okay, the square root of 37. Now I'll just leave this in compact notation to get the x by itself. I'm going to take away 4. And what I'll do here is I'm going to take away 4 on the other side too, but I'm going to have the subtraction of 4, or in this case negative 4, in front of the radical. And so negative 4 will go out. Now the compact answer for the potential solutions in x, we have negative 4 plus or minus the square root of 37. And if I look at itemizing, so we're going to have at the upper ends, we have negative 4 plus the square root of 37. And we have at the lower end, okay, we'll have negative 4 minus the square root of 37. Okay, so this is what we started out with, and so we have with our numbers. Okay, so these are not going to be whole numbers, but in exact terms, okay, we're going to have radical expressions in the square root of 37. Okay, so this is a little different case of what we have with the square root property of equality. And now just some more things to cover. I just want to mention, now we have on page 68, okay, and we have for number 40, okay, so you have 6v squared minus 30 is equal to 0. And if I isolate, okay, so again, we're just changing up the variables. Okay, and if I isolate the variable expression, so if I add 30 to both sides, okay, so I have 6v squared is equal to 30. Now look at dividing by 6. Okay, so instead of x, I'm working with the variable v. 30 divided by 6 is going to be 5. And so for what we had transitioning out, going from, just I go from x squared to x and going from v squared to v, the p-value we have at 5. And 5 is not a perfect square, so the exact results here are going to be where v is equal to positive or negative the square root of 5. And for what we have in the case of 41, this time we have the quantity. Okay, so we're looking at solving for k. And here's another situation where we are going to have radical reduction involved. Okay, so I have the square of k plus 2 is equal to 28. Okay, so you got the square of k plus 2 by itself, and we have equal to 28. And if I go from the square of k plus 2 to just k plus 2, to the right, and we have plus or minus the square root of 28. Now the square root of 28 can be lowered. Let me just mention, for the square root of 28, okay, the highest perfect square divisible into 28 is going to be at 4. 4 goes into 28 7 times. Okay, now, so you got 4 is a perfect square. Now the square root of 4 is going to be at 2. So the square root of 28 reduces to 2. Square root of 4 is 2. Square root of 7 is going to stay. So for what we're going to have here, okay, we're going to we're going to have k plus 2 is going to be plus or minus 2 times the square root of 7 and if I subtract 2 at both ends, and we'll do here on the right, I'm just going to move the subtraction of 2 in front of the radicals. Yeah, k plus 2 minus 2. So we have in compact notation, we have that k is equal to negative 2 plus or minus, okay, 2 times the square root of 7. And if I were to separate the answers, and I know Alex is big on this, we have at the upper end, we have negative 2 plus 2 times the square root of 7. And at the lower end, we have negative 2 minus 2 times the square root of 7. And those will be your results, okay. And we have just rounding out. Okay, one other technique. Okay, now when we had the quadratic equation in standard form, we had ax squared plus bx plus c is equal to 0. And if we're factoring by grouping, or even using the square root property of equality, might seem to fall short in terms of solving for x. We do have, as another resort, what is referred to as the quadratic formula. And this is used especially if the trinomial or the expression itself cannot be factored. And so you would have that x is equal to negative b plus or minus, okay, the square root b squared minus 4ac, 4 times a times c, all over 2a and I'll give you just a case here with the quadratic formula. So we have a trinomial that cannot be factored, but you have set equal to 0. Alright, you cannot factor this trinomial into integer coefficients. Okay, but you got your a is going to be at 2. Bx, we have 7x, so b is equal to 7. And for c, okay, c is going to be another 2. And in looking at solving, so if we utilize the quadratic formula, so we got square root of b squared minus 4ac over 2a. So negative b becomes negative 7 plus or minus, okay, the square root. Now b squared is going to be 7 squared minus 4 times a, which is at 2, times c, which is at 2, over 2 times 8. So you have 2 times 2. Now I'll just mention 7 squared. Okay, that's going to be 49. Negative 4 times 2 is negative 8, times 2 is negative 16. So that is going to be 33. So for x, we're going to have negative 7 plus or minus the square root of 33 all over 4. So that will be your compact result. And if you were to put separately, we will have negative 7 plus the square root of 33, everything over 4. And also at the lower end, we will have negative 7 minus the square root of 33, also over 4. and we will look into that other type of situation. Again, so you had the square root property of equality along with the zero product property, and we have with this most recent approach the quadratic formula.